In this research, we propose a planning framework for stable, robust multi-contact manipulation. Multiple robots can handle complex geometries and offer more payload than single manipulators. One example is multi-manipulator multiple pegging hole, which requires simultaneously aligning and inserting multiple pegs. Coordinating multiple robots is challenging, especially in maintaining stability during multi-contact manipulation. Avoiding slipping improves object manipulation by keeping the control force within the friction cone. Another challenge is sensor uncertainty. Assuming perfect accuracy, the optimal peg insertion policy would be collision-free. However, this policy often fails because the hole's actual position differs from the robot's estimate. Therefore, the robust policy to insert a peg is to slide along one side and insert compliantly. To address these challenges, our research introduces a planning framework tested on a 2D dual-arm peg-and-hold task. We use impedance control, where U is the robot's desire point, C is the contact point, and Z is the peg's pulse. We propose a cost function consists of 5 terms. The final cost estimates the distance between the peg's final pulse and the estimated target. The friction cone cost ensures the control force remains within the friction cone. Squeeze cost minimizes a needed control force to manipulate the object. The stability term ensures the manipulated object remains stable. Last term is regularization. Here is our planning framework. BBL select the optimal policy based on a cost function. The uncertainty of the whole is modeled as multiple scenarios G in parallel. Our goal is to select an optimal policy that minimizes the cost across all scenario distributions. Here is the performance of friction cone. Larger friction widens the cone, while smaller friction narrows it. The policy increases force to maximize friction and prevent slipping. We implement these policies in the real world 3 separate trials. Policy DMP 0.05 on plastic rubber contact surface. DMP 0.6 on plastic contact surface. DMP 0.05 on plastic contact surface. We know this DMP 0.6 failed with low friction experimental condition, while all the other scenarios succeeded. Theoretical analysis shows manipulation is stable if control forces don't cross the peg. Without stability cost, controls cross, leading to insertion failure. We then evaluate the robustness of our framework in both simulation and real world, testing dual-arm peg-and-hole and multiple peg-and-hole tasks with different chamfer size. A Kinova robot is used to vary the pose of hole, representing real-world uncertainty. Each setup has 20 trials. Our results demonstrate that our method effectively bridges the scenario gap, achieving high success rates in both peg-and-hole and multiple peg-and-hole tasks. For a detailed analysis, please refer to our paper.